Hi, welcome everyone. Here we go again with the second half of chapter 6. Again, you should have gotten the notes on Google Classroom for 6.3 and 6.4 together. But 6.3 is parametric equations. What parametric equations are is a set of equations with a third variable. Normally we just have x and y, but parametrics we have x, y, and t. And so x is defined as a function of t, and y is also defined as a function of t. So you're going to have two equations, one for giving you the x-coordinate and one for giving you the y-coordinate. And then t, the variable t, which is usually time, is the parameter in the equation. So here's what one might look like. So x equals t squared minus 2 and y equals 3t. Okay. So one of the ways to handle this is to set up a table of values, since we can kind of see what's going on as time passes. So I'm just going to do A right here. So it says time is greater than or equal to -3 but less than 1. So I'm just going to set up a table of values for this particular set of domain. X is t squared minus 2. So we can figure out all the x's with these different values of time. So -3 squared would be 9 minus 2, which is 7. -2 squared is 4 minus 2. -1 squared is 1 minus 2. 1 minus 2. Okay. 0 squared minus 2 is -2. And then 1 squared is 1 minus 2 is -1. So these are my different x values in the 5 different points that I'm going to graph. The y values will be defined as 3t. So we'll take our -3 and multiply it by 3, -9. -2 times 3, -1 times 3, 0 times 3, and then 1 times 3. Okay. So hopefully I did that correctly. And then we can kind of graph these. So my x's are going to go from 7, so 1, 2, 3, 4, 5, 6, 7. My y's go all the way 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 7, -9, 2, -6, -1, -3, -2, 0, and then -1, 3. Okay, so this is what I have so far, and if I were to connect those, I get that graph. And if we would expand our domain to have more t values on either side, I'm thinking we would get like a sideways parabola if I just had a few more values in my table. And I think that's what we would see in examples B and C. It would just give us some more. So I'm going to just guess that it would look like this, and we just get more of a parabola shape. Maybe with example C. But this gives you an idea what a parametric equation does. It gives you each x individually, gives you each y individually. You can put them together to get a graph. Okay? So if you can get a graph like that, shouldn't you be able to just write an equation of something like that? And there's lots of value in doing so, and just putting it back into a normal equation, like a y equals equation. That's called eliminating the parameter, or getting rid of the t. Right? So that's the next thing. I was like, okay, so how do I take these two equations and put it back to what we would consider a normal function? So it says eliminate the parameter, which means get rid of the t, and write it as just like a regular old function. So first thing I want you to do is solve one equation for t. You get to pick which one you want to, probably the one that's easier. So if I look at solving this one for t or solving for that one for t, I'm going to just pick this one. So I'm going to do x equals t plus 1, and I'm just going to subtract 1 from both sides, and I get x minus 1 equals t. Okay. Okay. So I have that. Then all we need to do is substitute that into here. Okay. So step number 2, substitute the above into the second equation. Okay, So I am going to take this x minus 1, it's now t, and I'm going to plug it right in there. So I have y equals 2t, and I will replace t with x minus 1. Okay. And then if we just distribute, we'd be like, oh, that's just 2x minus 2. Ta-da. So there we go. So now what we have is one function in terms of y and x. The t parameter has been eliminated, right? So what this is, it says to identify the graph, okay? So this is just a line, right? Y equals mx plus b. So that's your slope, that's your y-intercept, okay? In doing that. All right, so that's eliminating the parameters. Solve one of the equations for t, pick the easier one, usually the x. So take that one, solve it for t, and then plug it into the second equation. You'll get, in this case, a line, but you might get something other, maybe a parabola or something like that. Okay, so that's eliminating the parameter. We have a few more interesting problems in this section, but as you know, we're streamlining things, and so we're going to skip this one with the cosine and the sine. We're skipping that one. Also going to skip this one with the 5 minus t squared. Okay, so I'm just kind of doing the bare minimums here so you understand. But we do have an additional problem that is on your quiz. It's the baseball problem. I'm not sure if it's in your notes, but it's in mine. So make sure you pay attention to this one. So here's the deal. So Kevin hits a baseball 3 feet above ground with an initial speed of 150 feet per second at an angle of 18 degrees with the horizontal, with the horizon. Okay. Will the ball clear a 20-foot wall that is 400 feet away? Okay. So this is kind of what's going on, you know. So you got this dude over here, okay, and he hits this ball 3 feet off the ground. Right, so the ball's coming at him, he hits it with his bat, and then the ball, of course, is going to have this kind of trajectory or path. The question is, will it clear a 20-foot wall? So there's a wall over here. Okay, I probably should make it a little bit higher. Okay, that's 20 feet high. Okay, will it clear that wall, or will it hit that wall? Okay, it's 400 feet away. Okay, so we kind of want to just see, as time passes, what's going to be the path of this ball. Will it fall short? Will it go over? Kind of a thing. So we do have a setup for equations, and this is kind of the setup that you'll need for questions 43 and 44 and the one for your quiz. You'll want to look back at this. It is x equals 150. Notice what 150 is. It's how hard you hit the ball, okay? So that's what that is, okay? And then we have at the angle, cosine 18, okay? So that gets substituted in as well. So these numbers can change, okay? And then there's a t there, okay? And then you have a second equation, y equals negative 16t squared. This is the force of gravity, okay? Plus parentheses 150, that's your 150. Sine 18, okay, that's what 18 over there. The plus 3 is the 3 feet off the ground. That's from there, okay? So you're gonna need these two equations, right, when you set up your problem. So it's x equals, this is some kind of variable, this is some kind of velocity, times cosine, and then there's a theta here, times t. Okay, so you kind of have to set that up. So you have to put in that velocity, you have to put in this theta. Okay, so this is something that you're going to substitute in, and that's something you're going to substitute in. And then y is negative 16t squared. That's gravity, that doesn't change, plus, and then it's velocity again, how hard you're hitting it, times sine theta. Okay, so here again is where you substitute in, okay, for your velocity and your theta. Okay, and then it's plus the initial height. So plus, and I'll just say initial height. It might be on the ground, so that's a 0. Here it's 3 feet off the ground, so it's 3, right? Okay. So what we're going to do is we're going to use our calculator to see what this ball is doing as x changes, and then what's its height, y changes. So I'm going to try and do this on the calculator so you can see this. So this is the TI calculator. All right. So what we can do is we can change the mode on our calculator to work in parametric. So I'm just going to go to mode, and here we have functions, and we also have parametrics, if you can notice in your calculator. So I'm going to change function over to parametric. So if I arrow down and then just highlight parametric. And then when you hit your y equals, you have x in terms of t and you have y in terms of t. So you can type in these equations. I'll just retype them again. So it's, make sure you're using them parentheses. So it's parenthesis 150 cosine 18, close that parenthesis plus the outside parenthesis, and then t, which you get using your variable button down here. Okay, so there it goes. Right, and then I have that second one already typed in, but you can see it's just the same. So it's negative 16t squared. I guess I'll show you. Negative 16. T is here on the x key like it was before, squared, plus, and then you do want to use parentheses again, 150 sine 18 parenthesis t plus 3. I think I got that. All right, so we are not, there we go, trying to get this so you can see it. So we're not going to graph this, we're going to table this. Okay, so table is up here on top of the graph. So we're going to hit second graph for table. All right, and then we have t is time. So these are your seconds right here. At 0 seconds, nothing is going on the x-axis, but it's 3 feet off the ground. And that should make sense because that's where the ball starts. But 1 second later, it's 142 feet out, and it is 33 feet high. 2 seconds, it's 285 feet out, and it's 31 feet high. So it's giving you the path of the ball at each second. Okay, so the first piece of information we get is right here. It's like at 142 feet, but it's 33 feet high. Okay, and then the next second, it's, and I'm just kind of just guessing where these go, 285 feet out and 31 feet high. Okay, so what's going to happen as it gets closer and closer to being 400 feet out? And that's what you want to take a look at on your calculator. Okay, so if we go back to just a closer look, having trouble getting this so you can see it. So 400 feet out, at 427 feet out, it's below ground, right? It hit the ground already, so it can't really go below ground, but it has hit the ground. And so I want to just kind of zoom in. What's going on between 2 seconds and 3 seconds? So I'm going to do that in my table set, which is right above window, right here. So I'm going to do second table set. I'm going to start at 2 seconds. So I just changed that to 2 for my start. And then I'm going to just count by like a quarter of a second, 0.25. So I can just zoom in to see what's going on at some closer values. I'm going to go back to table. So at 2 seconds, I apologize, this is not the best here. It's 285 feet out and it's 31 feet high, which we know. Okay. But now when we get close to 2.75 seconds, it's 392 feet out, but it's only 9 feet above ground. Okay. It needs to be 20 feet above ground, right, if it's going to pass over this wall. Okay. And then we saw what's going on here. You could narrow in a little bit more if you needed to, but I can tell by looking at this at 392 feet out, it's only 9 feet above the ground. So I'm going to say, no, it's not going to clear this fence. Okay, and I wasn't, so this ball, if we just kind of, this is what it's doing, it's going to fall short of clearing that fence. Okay, and so we can see that it's, you know, not going to be a home run. So I'll just take my last value here, 392, which tells me that at 392, it's only 9 feet tall. So it's actually down here a little bit more. And so it's not going to clear that fence. Okay. So practice that in question number 43. I believe it has you use the exact same equations here. But I do have 44 as well as one for you to try. This question will be a quiz question, so you want to be able to table your equations, know this setup, okay? That's important. And so here's the assignment for you. Really short again. So number 11 and 21, notice on 21 you don't need to find the domain. That's part of the instructions, but you don't have to do that for our purposes. Okay. 43, that's a baseball problem. And then 44 is also a baseball problem. Because it's not in the back of the book, I put the answers right there for number 44. So you can at least check to make sure you're able to do that one correctly. Okay? Once again, good luck. You guys are doing great.